So this is part 3 of Unit 1, where we extend our discussion to quantum mechanics. So moving on from atomic theory, I mentioned at the end of the previous part about Heisenberg's uncertainty principle. So Werner Heisenberg won a Nobel Prize in Physics in 1932 for this work, where he showed that it's impossible to know simultaneously the exact position and momentum of a particle. That is, the more exactly the position is determined, the less known the momentum, and obviously vice versa. He developed an equation, okay, and the equation shown on the slide looks something like this. So this refers to position, and this refers to momentum. And he related it and said that this product must be greater than or equal to the ratio of Planck's constant over 4 pi. So referring to the spectral line example for hydrogen, we can measure the energy of the line quite accurately because the change in momentum is quite small, but the change in the position needs to be really large. Okay, so with quantum mechanics, we can't treat electrons as simple particles with their motion described perfectly. Heisenberg has just proven that we can't do that. We have to consider the wave nature of electrons that must be characterized by a certain degree of uncertainty in their location. We can only describe areas or regions that indicate the likely location of an electron or probable location. These regions are called orbitals. Okay, and if we have a very high probability of finding electrons in these regions, we're going to have a high electron density. Now moving on, another very well-known scientist by the name of Erwin Schrödinger. He won a Nobel Prize in 1933 for his work in quantum mechanics. Both he and Heisenberg made use of wave mechanics. Now, wave mechanics is simply mathematical descriptions of wave properties to describe the properties of electrons. So they developed the equation that describes the wave-particle duality, which means that the electron can have both properties of waves as well as a particle at the same time. The equation is based on a wave function. Okay, what is a wave function? You know, a function is like a mathematical equation, and the wave function was given the capital Greek symbol phi. This mathematical function is a position coordinates are describing the electron wave in space. Okay, so this wave function therefore also describes orbitals, and therefore different orbitals are going to have different energies and different wave functions. So the Schrödinger wave equation can be represented in several forms. One form that is quite appropriate for motion only in the x direction is given by this equation over here. Okay, so you can see it's quite a complicated equation, and the key elements that you need to take out from this is that m refers to the mass of the particle, E refers to the total energy, and V refers to the potential energy of the particle. Okay, now you need to remember that electrons don't just move in one direction, they move in three-dimensional space. So essentially the Schrödinger wave equation expands to this equation down here, which is quite a complicated thing. So each taking into account, so here we have for the x direction, and here we have the x, y, and z direction. The equation can be grossly simplified to state that we have h phi is equal to E phi. H is a Hamiltonian operator, and a Hamiltonian operator is simply a mathematical description and an equation, basically, which looks something like this. Consists of two parts. You can see there's a first part of the equation, which represents the kinetic energy, and the second part of the equation, which represents the potential energy. Another form of this Schrödinger equation, of which the wave function phi is a solution for an electron free to move in one dimension, is given at the bottom over here. Okay. Okay, so you need to remember a couple of things, that each wave function is representative of an orbital, and there are an unlimited number of orbitals and therefore an unlimited number of solutions to the Schrödinger wave equation. Each wave function describes the wave properties of a specific electron in a specific orbital, and the probability of finding an electron at a given point can be defined as the square of the wave function. Okay, that probability of finding the electron at a specific point is referred to as the electron density. All right, to understand how an electron actually moves, we can look at something called the particle in a one-dimensional box. The first thing we need to do is define the potential energy. So if we look at this diagram on the slide, we're going to see that the potential energy inside this box, okay, is going to be 0 between the position 0 and L along the x-axis. And it's going to go to infinity at the walls of the box. Okay, so we assume that the walls are going to have infinite potential energy to ensure that the particle has 0 probability of being at the walls or even outside of the box. Doing so is going to significantly simplify our later mathematical calculations as we employ these boundary conditions when solving the Schrödinger equation. The next step would be then to solve the Schrödinger wave equation, and we're going to use the time-dependent Schrödinger equation for a particle of mass m moving in one direction only. So remember that equation I gave you earlier that looks something like this. I've simplified the potential energy section of the equation over here. Okay. So this equation can be modified for a particle of mass m that is free to move parallel to the x-axis with 0 potential energy, resulting in the quantum mechanical description of free motion in one direction. So the equation simplifies to equation 2 on the screen over here. This equation has been well studied and gives a general solution, once we solve it, of this, number 3 at the bottom over here. So the general solution shows that the wave function is equal to a sine Rx plus b cos Sx, where the final solution of the wave function gives us this major equation over here, where we should be able to recognize something here, this value of n. Okay, these describe the energy levels. Remember, they are quantized, so go back to your first year chemistry, understanding what the word quantized means. It means energy comes in packets. And we know that we have energy levels 1, 2, 3, up till whatever. And of course, we called n the principal quantum number. So this is where the quantum numbers come from. All right, so let's have a look at now what these waves look like. They look like any kind of wave. And obviously, these waves can interfere with one another. So let's have a look at this first diagram here, where we have two waves. We've got the bottom wave and the top wave over here. Let me just put on a laser pointer for you so you can see what I'm talking about. There you go. So this is the bottom wave, and this is the top wave. And if we add the two waves together, the resultant wave gives us a big fat red wave. Okay, and in the bottom diagram over here, we have this top wave, and then we have this bottom wave here. If we add them together, we get the resultant red wave, because these two waves are now of opposite phase. Okay, so essentially what we can do is, if we take the wave function, okay, the function of this wave, and we square it, we end up with probability. So you'll see that this resultant red wave, when we square it, gives us the green wave over here. Okay, and we can then describe the probability density from this wave function over here. Remember that if we have a negative portion of the wave, when we square it, it becomes positive. So probability is then defined as electron density, and it just shows now the different phases and the probability density for those particular types of waves. All right, so let's have a look at a bit of a summary regarding quantum mechanics. We can look at Planck quantization of energy, where we know Planck's equation, E is equal to h nu, okay, where we got Planck's constant and frequency. We've got the de Broglie wave-particle duality, where we can include the mass and the velocity of the particle. We have Heisenberg's uncertainty principle, which takes into account the uncertainty in position x and the uncertainty in momentum, which is the change delta px. And then we've got the Schrödinger wave functions, where the Hamiltonian is the complicated mathematical operation, the phi is the wave function, and the E is the energy. Okay. And if we extend the quantum mechanical theory to the particle in the box, and we then are not only just looking at particle in the box in one dimension, but we move it to now 3 dimensions, the solved wave equations can then have 3 quantum numbers, which you are familiar with. So n will be the principal quantum number, L is the angular momentum, ML is the magnetic quantum number, MS is the spin quantum number, and I want you to go and refresh your memory on quantum numbers so that you know how they relate to the orbitals. You will be tested on this in your assessment, explaining what the quantum numbers are, and I don't expect you guys to know the mathematical values of the Schrödinger wave equation or how to solve the Schrödinger wave equation. I'm just giving you the information so that you can see how the quantum numbers were developed and how they tend to describe the movement of electrons inside the orbitals.